This is an example of ChiSquared goodness of fit, which is a model that's used to test a distribution for multiple variables here and to figure out whether or not the claim that we're given for a certain percentage for each of those values is reasonable or not. So this is used for data that we can count, or in other words, it's used for categorical data. So in this problem, we're told that 80% of a certain comic book cover are considered regular, 15% are uncommon, and 5% are rare. So suppose I get a box of 200 comics, and I notice that 170 were regular. So I'm making a little table here where I have my observed value, and this data is what I'm actually seeing for each of these categories: regular, uncommon, and rare. So I had 170, I had 20, and I know the total is 200. So just as a quick note, since I know that this should add up to 200, this remaining number has to be 10 because I was at 190 thus far. So just knowing these first two numbers, I could have solved for this last one. This actually tells me my degree of freedom. My degree of freedom is the number of categories that I need to know in order to know everything for this problem. In this case, that is the number of categories minus 1. So for this problem, I have 3 categories minus 1. I need to know at least 2 before I can solve for that missing third one. So this is what it should be. Let's compare this to what they're telling me. So out of these 200 comics, they say 80% should be regular. So to figure out the regular, I'm going to just look at 80% of 200. So I'm going to find these expected by taking the number that it's out of the 200 times the probability of each individual category. So 200 times 0.8 gives me 160. I thought it should be 170. I thought it should be 160. I got 170. I'm off by 10. Next one. 200, and they tell me this should be 18%. When I type that into my calculator, I get 30. I got 20 uncommon covers. I was expecting 30. I'm off by 10 again. Finally, rare. Well, just a quick check. 160, 190. It's out of 200. I'm missing 10. So this last number must be 10. I knew 2 of the categories, and I could solve for the remaining 1. They still give me the percentage, which is great, because then I can double check this by doing 200 times that 0.05 like they tell me. That still gives me that number 10. So for the null hypothesis, I'm actually testing multiple things here. I'm testing that the percentage of regular is equal to 80%, that the percentage of uncommon is equal to 15%, and the percentage of rare is equal to 5%. So I'm testing to see if this entire distribution is a good fit. The alternative hypothesis is going to be at least one of these proportions is not as claimed. So to make this thing be unfair, I just need to have one category be way off for me to be like, I don't trust this claim because I'm getting way less rare comics than I should be, or whatever the case may actually be for the data. Now this looks reasonably close. I'm only 10 off for each of these categories, but percentage-wise, if I'm off by 10 and I was expecting 30, that's like 33% error for that category. That seems like a considerable amount of error. My model chi-squared looks at that total error. So it adds, this symbol means add, each of the observed values from my table minus the expected divided by the expected. Now these would give me the individual percentages. So for example, I would be off by 10 for this category uncommon. Out of 30, that's 33% error. Now to avoid having everything cancel out on me, I'm going to square it to avoid getting any sign issues. Ultimately, I'm ending up with the chi-squared as a result here. So going through, First observed is 170, and I thought I should have gotten 160. Next one is 20, and I thought I should have gotten 30. So on each of these, I am taking my observed minus the expected, I'm squaring it, and I'm dividing it by the expected, and I'm just matching it up. 170 was 160, 20 with 30, and 10 and 10. I'm going to type this into my calculator and see what I end up getting. I end up getting a chi-squared value of something like 3.958 or so. Next step. When I'm trying to find the p-value, chi-squared will always be a right-tailed test. Chi-squared in general looks something kind of like this. This happens at 0. Your degree of freedom minus 2 is where this mound happens. In our case, our degree of freedom minus 2 is 0, so our picture is actually going to start at this mound, and it's going to kind of look like this, but I'm just going to draw this in general. You start at your chi-squared value, your test statistic, and it's that much or more deviation. So the p-value is the likelihood of the sample data are more extreme. Well, or more extreme means more variation, not less. So more variation on this side means that it's not close to the claim. If I'm close to the 0, this is telling me the observed value is close to the expected. If I'm way out here, this tells me the observed does not look like the expected. And I'm kind of somewhere in the middle, so I don't know what my p-value is actually going to be. But I do know that the setup's going to look like this every single time. Chi-squared CDF, whatever my value is, or more extreme. So it's a right-tailed test, so it's going to be shaded to the right, infinity. And then whatever my degree of freedom is. I'm going to show you how to do this using a couple different technology sources. But if you're using an 83 or 84, you're going to go second vars to find this. But it works just like the TCDF. If I'm using a TI-89, I need to be in my stat list editor. And then I'm going to choose F5 for distribution. And if I'm inside of GeoGebra, I'm going to choose probability when I open it. And then I'm going to go into the option for chi-squared. So let's start with the TI-83 and 84. This is the easiest to read. So second vars, chi-squared CDF. My lower value, that is my 3.958. That's my chi-squared. My degree of freedom for this problem was 2. So I have 3.958, comma, infinity. Anything that's largest, a whole bunch of 9s, for example, should do fine in lieu of having an infinity button. And when I type this in, I get a p-value of approximately 13.8% or so. So it's actually a pretty large p-value. Again, this process, I'm going into distribution. So I go second vars. I find chi-squared CDF. And on this calculator, it's got the actual symbol. I type in the low value, comma, the high value, comma, the degree of freedom. So if it doesn't have this nice print, I would just type in the number, and then the comma button's above the 7, next number, comma, and then the degree of freedom. TI-89. In the TI-89, I'm going into apps, and then stat list editor, and I'm choosing distributions there at the top, so I'm choosing F5. I'm working with ChiSquared CDF, and in this calculator it spells out that chi-squared for me. My lower value, that's this 3.958 number. My upper value is infinity. TI-89 actually has an infinity. It's in the green above the catalog, so you could do green catalog to get that to show up, or diamond catalog if you can't see the color green. And my degree of freedom is 2. This gives me a p-value, that's this first line, of 0.138. And let's see the same thing inside of GeoGebra. I'm opening up GeoGebra. I'm going into the option for probability. The default it starts with is the normal distribution. Normal distribution shows up a lot, so that's a pretty nice default. But I'm working with chi-squared. My degree of freedom is 2. So my picture for this, it actually starts on like that other side of the mound. So it's just this little curve. Now for the shade, I want this thing to be shaded to the right. It's a right tilt test, so I should see it look like this. And then I type in my chi-squared value in this little inside box here. And then the number it spits out is my p-value. My p-value is 13.8%. So no matter how I cut it, whatever technology I'm using, I'm still getting the same p-value. In your conclusion, fourth step of hypothesis test, because chi-squared goodness of fit is always a hypothesis test. If your p-value is low, the null must go. If you reject the null hypothesis, you have evidence that at least one proportion is not as claimed. If your p-value is large, like it is in our case, we fail to reject the null hypothesis, and we do not have evidence that the claim comic distribution is not a good fit. So we don't have evidence that it's unfair. This feels like a double negative sometimes, and it seems like, well, if we don't have evidence that it's not a good fit, then this must mean that we do have evidence that it is a good fit. But I would be careful, that's not actually how these conclusions work. A lack of evidence for one thing does not provide evidence for another thing. For example, if I flip a coin once and I get tails, that's not enough evidence. That's just one coin flip. That's not enough evidence for me to say that that coin is unfair. Likewise, that's not enough evidence for me to say that the coin is fair. So I conclude here that I don't have enough evidence to believe that I'm currently being lied to, but I might want to continue to test this if I truly think that the situation is unfair.